product rule. And, but yeah, I think pretty much, my larger point here is I know that this is kind of abstract and it would be better if I had like a concrete example for you at the moment to illustrate the abstraction. Sorry, I don't. But after you can, and you can understand why it's what you have to do. I mean, we have to use these local coordinate representatives in order to understand how to do calculations on this curved space, because we don't have some notion of calculus up there already. Well, that's where McNerney would disagree with me. He would just say use calculus on the ambient space and restrict it. I'm trying to describe to you how we can build calculus through the charts. And the point is, if we do it in this way, we get the usual rules of calculus, which means that we can do calculus on a curved space in this way. That's the deeper truth here that I'm attempting to impart to you. And the proofs, it's the same stupid thing every time. Every single one of these proofs is like, wrestle with the notation, reduce it to a regular partial derivative, apply corresponding property for ordinary partial derivatives. Every single stupid one of these proofs is that same argument. Check it out. You take the function, local coordinate representative, but the composite of a sum is the sum of the composites. That's the wrestling with notation part. And then ordinary sum rule, and then back notation, unwrestled, done. So, and I know that, I mean, it took me a while to really fully believe these calculations. If you don't believe them yet, that's cool. You don't have to believe. You just have to agree. It's like the new form of tolerance, right? You don't have to believe what they believe. You just have to agree with them. Let's see here, something like that. But this one here, so that this one will drive you batty. We have to come to terms with the fact that this is nothing more than UI. Once you come to terms with that, the fact that partial xi, partial xj is just Kronecker delta ij is direct consequence of the corresponding theorem for Cartesian variables. Here's the chain rule. So basically, we wrestle, so the definition, then the same trick we did in the calculation for Sam's lemma, or whatever we call it. You know, I inserted x inverse and x there, but that's this composed with that, where this thing is what? Where u1 of w is x composed of y inverse of that, right? So I'm looking at the composite of a function from Rm to Rn with another function from Rm to Rm. I forgot which m and which n, but it's the composite of functions on Rn. And so I can do the ordinary chain rule here, which looks like this in terms, these are actually this is the chain rule written in terms of matrix multiplication of Jacobian matrices. This is literally the matrix multiplication of two Jacobian matrices of the composite of two functions. Yes, Daniel?
Are you almost done?
Seriously? Wah! Wah! How dare you? Yeah. So anyway, ordinary. Whoa. Oh, I think it didn't survive. It wasn't you. You're gonna escape. Did you get hit? Did you get hit?
No. Did I what?
Did you get hit with the markers?
No.
No. Okay.
No, I was just drawing a picture, but I have like homework to do, and it's kind of like hard to focus.
That's cool.
Which I shouldn't be doing homework during your class or something.
Oh, well,
But anyways, so
not doing homework during class, that is a good rule to live by. But if it's not a class you're attending, that's an exception. So are you thinking about the math major, or?
Yeah, I actually want to be a math teacher, but I wanted to accomplish here because I wanted to see like your style of teaching
Oh.
compared to my calculus teacher.
Yeah, this is anomalous. This is not my usual teaching. This is a very exceptional class. I'm sorry.
Yeah, I was gonna say you guys are all like all on the same page. Like you understand each other very well.
So,
Maybe not.
some of us maybe have been roped in here.
Pretend to understand what you're saying, or like
They
the other way.
they understand some of what I'm saying. They'll understand more later when they do the homework.
Questions are because we generally don't understand everything he's saying.
Is it class over or class started?
If you want to see what calculus looks like here, at least as I teach it, I have a YouTube channel. If you go, I've taped like calculus 2, calculus 3, and you can look in there and see the website. It's oh, my name is my YouTube channel. You'll find it. James Cook is my name.
His website is supermath.info.
That is also true.
Those are the links to playlists.
So you can. I have tons of classes taped there. You can see what like apps.
Pretty much good. This isn't really like calculus class based on calculus. So, there are other calculus classes.
Is class done or something?
Class is not done. Cease with your questioning, young man.
Well, not ceased my questioning.
That's my son Daniel. He's misbehaving.
I thought he was just like a random kid who was like in here.
You see, what you should do is talk to Dr. Sprano if you can find him. He is the patron saint of math education. Would he still be here? I don't know. He might. Have you looked in the math department yet? Oh, it's closed now? No, I'm sorry.
Were you at the Elmo house?
Did I what?
Were you at the Elmo house?
No. I just went to like 5 classes today.
I'm pretty sure Dr. Ball is still there.
That's okay. So anyway, another thing we can take from that is you can rewrite the partial derivative derivations with respect to one coordinate system with respect to the other by just taking this particular sum, and these are this is actually the kjth component of the Jacobian of that transition function. If you actually, that actually has to do with, I forget which one it is, but it's either x composed with y, or it's y composed with x, and I need inverse on one of those. Which is it? This one. So the Jacobian of these maps, one of the other, I think it's this one. The Jacobian of this transition function is got that matrix. And that matrix is what relates the partial derivatives in one coordinate system and the other. This is a relaxing proof. Why is a constant function is 0 under a derivation? Well, you can take any function and multiply it by the function which is always 1.
I need to go bathroom.
Did he I saw you wincing in pain, and I was worried it was
Oh no, it's not here.
some projectile. Go on. Take your time.
It's just the appendicitis.
It's the appendicitis. Uh-oh. If you let g be the function which is always 1, then fg is equal to f, right? But you can apply the Leibniz rule to fg to get that. But g is always 1. So since g is always 1, that's just x of f, right? So you've got x of f, c times xp, right? So that means that c times xp is 1. So you can bring the c inside and just get that xp of the constant function c is 0 rather. So I don't know, I like this. This is a welcome relief after fussing with these silly, coordinate maps. And I think I've really failed to make my point today. The point I'd like to make to you guys is that we can calculate on curved spaces with respect to these coordinate charts in the natural way. Like, once we sort through the formalism, it basically just says you write down formulas in terms of coordinate charts, and you just do regular calculus on it. At the end of the day, that's all I'm saying. But it takes me a while to really flesh that out. And I haven't done it yet. So this is the big theorem, and this theorem is I just never get as far as I want to, do I? I just have to come to terms with this. But so proposition 10.2.8 has what? This says that if we have two functions are equal for all x in some, I think V should be an open set about P, right? I think it should be an open connected set containing P, pretty sure. It seems to be missing from my proposition, but it seems kind of important. What's this V? Where are we taking x from, right? But anyway, so if you have that the two functions are equal, then xp of f will be equal to x. So then the derivation of f will be the derivation of g. It's just the same. And so that's a pretty, this is almost like a calculus 1 proof, right? F of x equals g of x means h of x, which is identically 0, is their difference. But we already know that, you know, the derivation acting on 0 gives me back 0. Consequently, xf minus xp of f minus g is 0, and consequently, the derivation of s equals derivation of g. Fine. You need these two things in the nuts and bolts of the proof of some of the things which follow, I think. So here's the big result. If you have a derivation on a manifold, you can write it in terms of the partial derivatives with respect to the coordinate derivations on the manifold. So like if you have the coordinate chart, if it's a three-dimensional manifold, to calculate the formula for a derivation, you just let the derivation act on the coordinate functions, and that picks off the components, and then that weights the sum of the partial derivatives. So like this one, let's see here if I can come up with an example. Well, no, let me not, I'm almost out of time, so let me shut up with my examples. I'll try to do examples next time. So here's that's the proposition. To prove it, it's actually not that easy to prove this. And you need a lemma, and this is the lemma, that if you've got a smooth function and you've got a chart which contains the point we're interested in, and we can just assume that we've got the chart centered so that the point is at 0. That's not a severe restriction, because you can always redefine the chart by just shifting the image, right? If x of p was q, you can define anew like x tilde of p to just be x of p minus q, and that'll shift the image of p to 0. So it's not a big deal to assume that p maps to 0 in the chart. Then there exists smooth functions g sub j from the manifold to the reals whose values at p satisfy partial f partial xj at p. In addition, for all q near p, we have this formula. So this is not quite a linearization result. This is kind of a sneaky theorem, right? It's saying you can write the function f of q is equal to f of p plus the coordinate functions at q, right? And then there's these other things, these gj's of q, right? Notice that gj of q is not the partial derivative. It's some function that when you plug in p, it's the partial derivative. But I'm not saying it's the partial derivative at all q. It's just the partial derivative at p. This is something very sneaky. I think this is the first in a series of results which go to what's called this calculus developed by Cara Theodori. But anyway, this is a quite technical result, and this is actually in McNerney. So this is what I was hoping to get to today. This is the thing I told you about. That I prepared for today. that I wanted to prepare for today. Someone insisted on I playing pool today. Distracted me slightly from my preparation for some reason. But I welcome the distraction. But I'm just trying to tell you where this is. So this is lemma. So his theorem 3.4.5, all right? And then his lemma 3.4.6 on page 93 of the text. That's where he does this. And he actually has the details of that lemma. Page 93 to 94. He has this lemma. Proved for Rn. Technically, then you have to take that and lift. Come on, what?
Perfect timing.
How do you stop? There we go. Daniel, go to the back, please. This is not an easy thing to prove, but once you have it, it's fairly easy to prove that any derivation is a sum of the partial derivatives. So the way it goes is, so I take my f, I replace it with my handy-dandy reformulation of f in terms of these g's, which somehow capture the tail of the Taylor series all into a function. Yeah.
What do you mean by Q near P?
Q near P.
Like, is there a notion of distances?
That means there's an open set which contains Q. Yeah. There's a connected open set in which Q is found. Yeah. And it has to be close enough to P that it's within the domain of the chart that we're considering. There's that. So I replace f with this formulation of f, and then I have xp f of p plus that, because it's a linear, right? It's a linear transformation, so I can do that. And then what's this next step here? Oh, what's f of p? What? It's 0, right? It's a constant. So the derivation acting on a constant 0. So that we need that lemma right there. That's gone. Now, what's that?
Product rule?
Yeah, product rule. Very good, Travis. So this is the product rule because we've got that times that. So it's, xp acting on xj, xj times xp acting on that. And then, let's see what's next here. What did we assume about, we assume we have a coordinate system where xp is what? What's this? Remember, x of p is 0. So the jth component of 0? 0. So this piece is gone, and we're just left with that. And then when we plug in p, this is supposed to all be evaluated at p. That somehow got lost. Right here. That's supposed to be p. Is that what your question is? Somebody had a question.
Oh, somehow the xj of q turned into xj of p.
That is the Leibniz rule. It says, Leibniz rule says you differentiate and then you multiply by the function. I could say it in words or I could just write it. I think it would be faster, like way faster to write it. So xp acting on fg is equal to f of p, xp acting on g, plus g of p, xp acting on f. So you evaluate. Yeah, that's a typo. That should be, or it's just a plain old error. But that should be a p. And that, by construction of the lemma, is partial f, partial xj.
So xp of gj q is supposed to be xp of gj.
This is gj.
The other constant. xp of gj q
Yeah.
is supposed to be xp of gj only.
Well, this is the abuse of, I mean, maybe that's also true for this too, right? It's this question we always have when you're differentiating. Do you say derivative of f or derivative of f of x?
So in this case,
So if you're going to delete q from here, I should delete it from here and here too, right? I think it's important to put it here because it emphasizes the distinction between the f at the start. I mean, I guess I could say f of p plus that without the q, and it wouldn't be wrong. Yeah, I know what you're asking. I don't have a good answer. So there you go. That shows that any, no, Dan, no, we're not done yet. Derivation can be written as, we are close to done, yes, but every time you ask me if we're done, it adds 2 more minutes. Now, when we study this lemma from McNerney to prove that you can rewrite the function as f of p plus these gj's of q, right? Like I just did, times the coordinate functions. In that derivation, there's a step where you need smoothness of the function. That calculation breaks down if you try to do it for just so many times differentiable functions. And it's actually the fact that we're working on the function space of smooth functions that means that the set of derivations of these smooth functions is m-dimensional here. If you work with the set of derivations on not smooth functions, but say twice differentiable functions, that set of derivations is infinite dimensional. So the smoothness is actually important to the lemma.
Is that the thing you were mentioning a few minutes ago about derivation?
Yeah, well, that's just, for me, that's just kind of interpretation. But I'm sure it's related to why that lemma breaks down in that case. Now, if you think about that, it starts to make sense to you if you really start thinking about it. What does it mean to say a function smooth? Like, how many conditions on function space is it to say a function smooth? I mean, it's not that one derivative exists, or 2 derivatives exist, or 3 derivatives exist. It's that infinitely many derivatives exist. So, I mean, yeah, function space is huge, right? But I don't know. So, well, that's not a very good analogy. I mean, the derivations, anyway, derivations on smooth functions are finite dimensional, whereas if they're not smooth functions, then I think we lose derivations as a characterization of the tangent space. So anyway, long story short, I've now hopefully somewhat carefully described to you what derivations are, and that's our first, and in fact our central way of looking at a tangent space. It's the set of derivations on the manifold. So really, a tangent space to us, it's a set of partial derivatives on the manifold. It's all the partial derivative operators on the manifold. That's what it's capturing in terms of the calculus. I actually went over this last time, but this is my 2 cents about how do you view that. So this is the directional derivative, right? So it's this, but that's this, so you can identify ABC with the derivation, A partial partial x, B partial y, C partial partial z. And so that's the interpretation. When a derivation xpx on a smooth function f, it describes the rate at which f changes at p in the ABC direction. So there's this geometric interpretation of these derivations, in addition to the algebra, which is beautiful, and the fact that it abstracts calculus. The fact that it abstracts calculus to the curve space, to me, is what's most interesting. And then here's where I started to talk about last time. How we can talk about the differential of a function pushing tangent vectors on one manifold to tangent vectors on another manifold. So anyway, yes, Samuel, I will, Sam rather, I will post these. And just to show you where we're going with them, these things are actually all in McNerney. And actually, when we get over here to differential forms, we're then in what? We're in his next chapter. So I'm going to try to more or less follow these notes, but I want to do some things. I want to try to add examples to make more sense. I, of course, need to give you guys homework questions to try to help you understand better. I'm not being super technical here either, right? Like every question Kang asks, I can't answer carefully. You know, he keeps asking me what I mean by near. I'm not going to really answer you. And I'm going to try to not let this drag on too long. Really what I want is for us to leave this part of the course with an understanding of this is what a manifold is conceptually. This is what a tangent space is conceptually, right? And this is how I can calculate with derivations, how I can push. The next thing we talk about is the push forward, which gives us a way of taking derivations on one manifold and pushing them to another. I actually have a concrete interpretation of that in terms of a calculus 3 thing we did. You may remember we rewrote like partial x in terms of partial r and partial theta. Doing that is actually pushing derivations from one thing to another. You can look at for another day, but I can actually make a connection with calculus 3 and some of the calculations we did there, interpreting them in terms of what we're doing. And hopefully we have enough understanding that when we do differential forms, it's not just abstract nonsense. Although it may feel like abstract nonsense at the moment. I still need to give you more examples of manifolds, I think. I will post both of my notes. I have this one, which is what? What are we looking at? Are we looking at 2013? 2011 is also good. I actually have, and here's some neater examples, like here's the Mobius band, and it's, as you can see, slightly incomplete. Some of the same examples here, but I will post both the, oh man, so my 2011 is actually where I have some discussion of the equivalence between equivalence classes of curves and derivations, which I'm torn about whether or not I should actually do that in here. I think it will hurt Travis if we do it. But are you busy? You're busy. Okay. Yeah. Well, I may do some hurtful things, but anyway, I will post the 2011 and the 2013 notes. I was doing 2013, right? 2013 notes was I doing today. 2013 is like you'll see that it's a refined version of 2011, but at the same time I've chopped some things out. So they're both, I can't make up my mind in here. What can I tell you? All right, I'll shut up. I've talked long enough today. I've talked too long. It's all Daniel's fault. Yes, it is. You can hit it, Jonathan. Thank you.